This is part 3 of section 4.1. We have talked about graphing, we've talked about the substitution method. Now we're going to talk about the elimination method. This book calls it the elimination method. The college algebra book calls it the addition method. And I like both names because they really do tell you exactly what you're going to do. What we want to do is we want to be able to add two equations together and eliminate a variable in the process. Okay, and we can do this by multiplying one or both equations by the number that will make a variable go away. We're trying to force a number and say in front of x to be -3 and 3 or -10 and 10, something that when we add them together they will cancel out. Okay, so let's look at this first equation, first system. What we're going to do is we're going to imagine adding these together, combining like terms, and we want a variable to go away. Right now, if I added these two together, I would get a -6, here a 4, and I'm not worried about these going away. I'm really, on my first steps, concentrating on the variables. Now, we are allowed to multiply an equation by any number other than 0, and it's still the same thing. So it would be fairly easy to change this number right here into a -3. Now, why did I choose this? Only because when you don't have a coefficient, it's the easiest thing to change. It's the easiest thing to match. Okay, so I'm going to multiply this entire second equation by a -3. Okay, so this will become, I'm recopying my first equation. Always be really careful on a recopying step. It is a great place to make a stupid mistake. Now I do need to multiply everything here. -3 times -4 will be +12x. -3 times 1 is -3y is equal to -3 times -3, which is 9. Now if I had to pick out the most common mistake on this type of problem, is that people remember to multiply this and this, but they don't remember to multiply the constant. Everything has to be multiplied. So this equation is the same as that one. This equation is this one transformed. Now if I add these together, -2 plus 12 would combine to 10x. -3y and +3y cancel out, and that's what I wanted to happen. It did not matter which variable I did this to, I just needed one of them to cancel out. And this equals 1 plus 9, which is 10. Now we're back in the same step we were essentially with substitution. We have an equation with only one variable. We go ahead and solve that, dividing both sides by a 10, and you get x is equal to 1. Okay, now we back substitute just like we did before. To me, it looks like this is going to be the easiest one to find y, and that's only because it doesn't have a coefficient right there. So take this 1 and plug it in here. -4 times 1 plus y is equal to -3. So -4 plus y is equal to -3. So I need to add 4 to both sides. And when I do that, I get y equals 1. So if I were to graph these two lines, they would cross in the point 1, 1. That's the only combination of numbers that satisfy both of them. Okay, so now let's look at this one. It's a bit harder. I want to make a variable go away. It does not matter which one. We got rid of y above, so I'm going to choose x. And that's the only reason I'm choosing x here is because, is so that, just because we didn't do it on the other one. What I want to do is I want to, again, make these numbers match, but have opposite signs. It's a lot like finding a common denominator. There's nothing particularly easy here. I could multiply this by a fraction and make this go away. Same thing here. It's not quite that easy to do. So I'm going to multiply both of these by something. If I were thinking common denominator, a 4 and 3, I would be changing these into 12s. That would be my common denominator. So I'm going to change these into 12s. To get a 12 here, I need to multiply by 3. To get a 12 here, I need to multiply by a 4. Now, right now, that gives me positive 12s on both of these. And I really need them to have opposite signs so that when I cancel them out, so when I add them, they will cancel. So you can make either one of them a negative. Let's I don't know, make the -4. It works out either way. Now I need to multiply everything here by a 3. That will be 12x plus 9y is equal to 3. Now multiply everything here by a -4. -12x minus 8y is equal to -8. Now add these together, your 12s cancel, and you get y is equal to -5. Now take this value and plug it into either one. We've been plugging into the second one on the other problem, so let's do the top. 4x plus 3 times y, which is -5, is equal to 1. So 4x minus 15 is equal to 1. Add 15 to both sides. You get 4x is equal to 16. Divide both sides by a 4 to get x is equal to 4. So your answer here would be the point 4, -5. Again, x and then y, not the first answer and the second answer. Okay, one more. I have 2x plus 3y equals 7, and -4x minus 6y is equal to 14. Now we just need to pick a variable to get rid of, so let's say we're going to get rid of x again. Ignore your signs for a minute. I have a 2 and a 4. If these were common denominator, I would be trying to create a 4, correct? So if I multiply this top equation by a 2, I'll have a 4 here and a 4 here. Now look at your signs. If I'm going to end up with a +4 here and -4 here, that means I don't have to worry about my signs. So multiply the entire second equation by a 2, and you get 4x plus 6y is equal to 14. And then -4x minus 6y is equal to 14 because we didn't need to change our second equation. Add these together. That cancels and that cancels. So both of our variables went away, so I know I have a special case, and that just gives me a big old 0 on the left. Now add up the right and you get 28. Now remember, our special cases depended on whether or not what we ended up with was true. 0 does not equal 28. This is false. Okay? If your variables end up canceling out and you end up with something that is false, we call it an inconsistent system. It has no solution. We can use the empty set. So this is inconsistent system. We use the empty set to talk about it. It has no solution. And we know they have no solution because they are parallel lines. That's a lot of information we know about two lines just by doing what was essentially a very tiny little bit of algebra here.